Hello students, today I am going to discuss Ohm's law. In 1826, George Simon Ohm expressed a relationship between potential difference between the ends of a conductor and electric current flowing through a conductor termed as Ohm's law. It states that the current flowing through a conductor is directly proportional to the potential difference V applied across the ends of the conductor provided the physical conditions such as temperature remains constant. That means when we are going to write it in expression, it is current proportional to potential difference, or we can say potential difference is proportional to current. When we will remove the proportionality sign, there will be a constant, that is R, which is known as the resistance of the conductor. This relationship is expressed by a straight line when we are going to plot a graph between potential difference and current. There are various factors on which this resistance depends. One is the resistance is directly proportional to the length of the conductor, then the area of the conductor, the nature of the material, and temperature of the conductor. Let us deduce Ohm's law by drift velocity. For this, let us consider a conductor of length L, area of cross section A. When a potential difference V is applied across the length of the conductor, the electric field is given by the relation E is equal to V upon L. As we are aware that the electrons are going to move towards the positive terminal of the battery, that is the direction opposite to the force F due to the applied electric field, the acceleration will be given as A is equal to F upon m, where m is the mass of an electron. If we put down the value of the force here, F is equal to E upon m. Now put down the value of E, electric field, from above, we will get it as EV upon m into L, where E is the charge of an electron. As the average thermal velocity of electron is 0, the drift velocity becomes A tau, where tau is the average relaxation time. Putting down the value of A from above, we get drift velocity as EV upon ml into tau. Also, the relationship between current and drift velocity is expressed as I is equal to NeAVD, where N is the number density of electrons, Vd is the drift velocity, A is the area, and A is the charge of an electron. Putting down the value of drift velocity from above in this current relationship, we get this equation. Now again we are rearranging this I and V relationship so as to form a ratio V upon I, which is nothing but the resistance of the conductor. The expression shows us that V upon I is equal to ml upon Ne square A tau. Now we are here in a position to define what is resistance. It is defined as the ratio of the potential difference applied across the ends of the conductor to the current flowing through it, that is V upon I. Or in generalized way, we can express electrical resistance as obstruction offered by the conductor to the flow of electric current through it. Also, we can calculate its SI unit. The SI unit is ohm, which is nothing but volt upon ampere, that is the SI unit of potential difference is volt and the SI unit of current is ampere, that is volt upon ampere, or simply it is ohm. The resistance of the conductor depends upon its dimensions, that is length and area, also the nature of the material, but keeping the temperature constant. Therefore, when we increase the length of the conductor, the electrons have to travel a longer distance. and hence they are going to suffer more number of collisions. Therefore, we can say that as the length increases, the resistance will also increase, or in other words, resistance is directly proportional to length. And when we decrease the area, the free electrons finds more difficult to pass through smaller cross-sectional areas. So, the resistance increases. Hence, if we combine the above two, we find that the resistance is proportional to length upon area. And if we remove the proportionality sign, there is a constant term known as resistivity or specific resistance. If we put down the value of length and area as 1 each, that is length is equal to 1 meter, area is equal to 1 meter square, then the resistivity comes out to be equal to resistance. So, resistance of a unit length with unit area of cross section of the material of the conductor is called as specific resistance, and its SI unit is ohm meter. That means we are simply calculating the SI unit by the formula R is equal to rho L upon A. The SI unit of resistance is ohm. We have to calculate the SI unit of rho. Length SI unit is meter and area SI unit is meter square. That means the SI unit of resistivity is ohm meter, which we have written here. Electrical conductivity sigma, it is the reciprocal of the resistivity, that is sigma is equal to 1 upon rho. As it is the reciprocal of resistivity, its SI unit will also be the reciprocal of the SI unit of resistivity, that is here it will be mho per meter. Effect of temperature on resistance. See, we have just calculated the value of the resistance from our previous slides, and we found that the resistance is equal to V upon I, which is equal to mL upon NE square A tau. If we view it carefully, all the terms, the mass of electron, length of conductor, number density, charge, area, all the terms are constant terms. Only one of the term is variable, that is tau, that is the resistance is inversely proportional to tau, which is the average relaxation time. Now let us understand what happens. When the temperature of the conductor is increased, the atoms or ions vibrate with more amplitude about their mean positions, and hence when they are going to vibrate with greater amplitude, their frequency of collision will also increase. And if the frequency of collision will increase, definitely they will reduce their average relaxation time, because what is average relaxation time? It is the time between successive collisions. If the average relaxation time decreases, definitely resistance will increase, as it is inversely proportional to resistance. Also, we can express the resistance of the wire in terms of temperature coefficient of resistance, that is R is equal to R naught 1 plus alpha T, where R is the resistance of the temperature at T degree Celsius and R naught is the resistance at 0 degree Celsius, and alpha is the temperature coefficient of the resistance of the material of the wire. See, we have discussed that there are various factors on which resistance depends. So, this is the effect of temperature on resistance. Now, we are aware that if we put length and area as 1 each, then resistance is proportional to resistivity. So, putting down the above relationship in terms of resistivity, it will become rho is equal to rho naught 1 plus alpha T. See, for metals like copper, silver, etc., this alpha, that is temperature coefficient of resistance, is positive. Therefore, resistivity of metals increases with the rise in temperature. This resistivity depends upon the nature of the material and temperature, while the resistance depends upon the dimensions, that is length and area. We use copper, silver, aluminium for making connecting wires because The reason behind is that they have low resistance or low resistivity, and hence current can easily pass through them. There will be less losses. While resistivity of alloys like nichrome, manganese is high, hence they are used for making standard resistors. So I have represented here the resistivity and temperature relationship of an alloy and the resistivity and temperature relationship of copper also. Similarly, the semiconductors and for semiconductors and insulators, this alpha, that is temperature coefficient of resistance, is negative. So the resistivity will decrease with the rise in temperature as is shown by the graph. Now there are few limitations of Ohm's law also. Like those devices which do not obey Ohm's law are called non-ohmic devices. For example, diodes, transistors, which we are going to study in our later chapters. The value of the resistance is constant for ohmic conductors. That means the devices in which Ohm's law is followed, on those devices the value of the resistance is constant. But those devices exist like diode and transistors in which the resistance is not constant. Such devices are non-ohmic devices. Or in other words, we can say that their VI graph, that is potential difference and current graph, is also not a straight line. So non-ohmic devices are also known as non-linear devices. That means V and I relationship is not linear, and even it is not unique, as is given by the graph of a diode. Also for the gallium arsenide. But such materials are also widely utilized in electronic circuits. Thanks for watching. Please like, share and subscribe.